The last sections in this chapter are looking at the chemical processes occurring during electrolysis. We will recognize the factors that determine which substances are oxidized and reduced at the electrodes, and then relate the quantity of a substance oxidized or reduced to the amount of current and the time that current flows. So far, we've described electrochemical cells that use product-favored redox reactions to generate an electric current. Equally important, however, is the opposite process, electrolysis, the use of electrical energy to bring about chemical change. Thus far, we've really focused on the galvanic cell, and we know that our anode is on the left, and that's our negative end. Our cathode is on the right, and that's our positive end. Energy is released by spontaneous redox reactions, and it's converted to electrical energy. We have our oxidation half reaction going from 0 to positive, so our electrons are on the right. We have our reduction half reaction where our electrons are on the left because we're going from positive to 0. So we've been gaining electrons because reduction is gaining. We have our overall cell reaction, and we have our electrons going from the negative end to the cathode, which is the positive end. But then our electrolytic cell is the opposite. We need electrical energy to drive the non-spontaneous redox reaction. Notice it looks pretty similar. Our anode is still on the left, the cathode is still on the right, but notice the difference. Our anode is no longer the negative end, it's the positive. So we have electrons being forced from the positive end to the negative end instead of what's naturally wanting to happen where electrons go from negative to the positive. All electrolysis experiments are set up in a similar manner. We have the material to be electrolyzed, either a molten salt or a solution, and it's contained in an electrolysis cell. As was the case with voltaic cells, ions must be present in the liquid or solution for a current to flow. The movement of ions constitutes the electric current within the cell. The cell has two electrodes that are connected to a source of direct current voltage. If the applied voltage is high enough, chemical reactions occur at the two electrodes. Reduction occurs at the cathode still, with electrons being transferred from that electrode to a chemical species in the cell. And oxidation occurs at the anode, with electrons from a chemical species being transferred to that electrode. Electrical energy is used to carry out reactions that are otherwise reactant favored, and this electrical energy is coming from an external source, like a battery. Notice the difference here in our electrochemical cell is that we have electrons moving from the positive anode to the negative cathode. So electrons are going in the opposite direction thanks to that battery. Let's look at the quantitative aspect of electrochemistry. Let's consider the electrolysis of aqueous silver ion. So we have silver going to solid silver, and obviously I need an electron on the left to balance that out. So 1 mole of electrons, if I look at my stoichiometric ratios, 1 mole of electrons for 1 mole of silver. I'm then able to look at current flow and time and how that yields moles of electrons. So current is equal to the charge transferred divided by the amount of time that happened in. And amp is how many coulombs per second. It is important to note that 1 Faraday is equal to 96,500 coulombs per moles of electrons. This is going to be important so that we can relate charge to moles of electrons. For instance, if I was told that it took 1.5 amps of current that's passed through silver plus solution for 15 minutes, we could figure out the mass of silver metal that's deposited at that cathode. What I can do is start with the 15 minutes that it took, and I'm going to go from minutes to seconds so that minutes can cancel out. There's 60 seconds in a minute. If I know how many amps, amps tells me how many coulombs per second are being passed through that. So I can then get rid of seconds, leaving me with coulombs. We can then take that 1350 coulombs, and knowing what that Faraday is equal to, that 96,500 coulombs per moles of electrons, I can have my coulombs as the denominator for moles of electrons. I can then look back at my balanced stoichiometric ratios and say that for 1 mole of electrons, 1 mole of silver is being deposited, And then finally, I can look at my molar mass on the periodic table, and I can say 1 mole of silver has 107.9 grams of silver. That will let me see how much silver is deposited, which should be 1.51 grams. Using that same process, see if you can solve this problem. First, we can calculate the charge, the number of coulombs that's passing through the cell in 30 minutes. To find charge, we can do current times time, or we can just start with that 30 minutes, times that by 60 seconds in a minute, and then times that by 2.4 amps, which is also how many coulombs per second. So all of my units would cancel except for coulombs. I can then take that coulombs and times that by Faraday's law, that's flip-flop, so that coulombs can cancel out, leaving me with moles of electrons. Then I need to look up here, and to go from copper 2+ to copper, solid copper, we needed 2 electrons to cancel out that +2. So we can then take that moles of electrons and say, well, 2 moles of electrons for every 1 mole of copper. And then look at the periodic table. 1 mole of copper has 63.55 grams of copper, leaving me with 1.42 grams of copper. Given the electrolysis of water reaction, calculate the mass of oxygen produced using a current of 0.445 amps for a period of 45 minutes. See if you can set this one up. First, I'm going to do my current times time, so 45 minutes, and then there's 60 seconds in a minute, and then times that by my 0.445 amps, which is how many coulombs per second, leaving me with just coulombs. And then I'm going to times that by 1 mole of electrons is equal to 96,500 coulombs. There are 4 moles of electrons for 1 mole of oxygen, and 1 mole of oxygen is 32 grams of oxygen. So I should get 0.1 grams of oxygen. And finally, let's look at how oxidation-reduction reactions are responsible for the corrosion of metals. Corrosion is the deterioration of a substance, usually a metal, in the environment by a product-favored oxidation-reduction reaction. Some examples are the tarnishing of silver and the conversion of copper to an attractive green patina. We can see here the corrosion that's happening here. Let's look at the mechanism of corrosion of iron in more detail. Air and water are reactants in this process. Both are sufficiently strong oxidizing agents to oxidize iron. So rusting, oxidation, is expected to be a product-favored reaction. Here's just a visual looking at 2 iron nails. And in this electrochemical cell, the regions of stress, the ends and the bent region of the nail, act as anodes, and the remainder of the surface serves as the cathode. Here's an interesting fact for you, the economic costs of erosion. It's estimated that corrosion-related expenses cost the United States economy over $500 billion per year. This includes the costs of corrosion prevention as well as repairing and replacing corroded products. Here's a look at the corrosion of iron in the presence of both oxygen and water, but other substances in air and water can assist in corrosion. Chlorides from, let's say, the sea air or from salt spread on roads in winter are notorious. Because the chloride ion is relatively small, it can diffuse into and through a protective metal oxide coating. Here are some interesting ways to protect metal surfaces from corrosion. There's many methods for stopping a metal object from corroding. Some are more effective than others, but none totally successful. The general approach is to inhibit either or both the anodic and the cathodic processes. Anodic inhibition is an attempt to directly prevent the oxidation reaction by painting the metal surface or by allowing a thin metal oxide film to form. Phosphating is another inhibition method of protecting metal surfaces. It involves treating the metal with an acidic solution containing dissolved metal phosphates. Phosphating creates a thin metal phosphate coating on the surface of the metal. These coatings adhere well to surfaces and have low solubilities in water and directly provide protection against corrosion. Cathodic protection is another way to inhibit metal oxidation by forcing the metal to become a cathode instead of the anode in an electrochemical cell. For example, galvanized iron. So this is iron that's been coated with a film of zinc. Zinc coating forms a sacrificial anode. And over time, the zinc reacts with oxygen and water to form zinc hydroxide, which adheres to the surface and continues to protect it from corrosion. So as you can see, there's a lot of chemistry that goes into protecting things in our environment from corrosion.